In this video and the next, I'd like to compare doing a calculation in spherical coordinates and in cylindrical coordinates. Here's the basic setup. Let's let Q be the snow cone shaped solid bounded above by the sphere x squared plus y squared plus z squared equals 4, and below by the cone z equals the square root of x squared plus y squared. I want us to set up, but not evaluate, the triple integral over this solid Q of z dv, first of all in spherical and then in cylindrical coordinates. In this video, I'd like us to get an idea of what the solid looks like and do spherical coordinates, and then the follow-up video, we'll set it up again in cylindrical coordinates. So first of all, let's see what this shape is. It lies below a sphere, so x squared plus y squared plus z squared equals 4 is a sphere of radius 2. And z equals the square root of x squared plus y squared. If we square both sides of that, we get z squared equals x squared plus y squared. And we recognize that as a cone. Since we're taking only the positive square root, then that means we're only going to get the upper half of the cone. So the vertex is at the origin, and the cone goes upward like this, and it will intersect the sphere in a circle. So I want the shape which has the sphere as its top surface and the cone as its bottom surface. So erasing some of the extraneous stuff here. That's kind of the shape we have. And if you had a raspa or a snow cone, then you can see why I'm calling this a snow cone shape. This would be like the little V-shaped paper cup, and this would be the ice on top of it. So let's see how we could set this up in spherical coordinates. Let me just recopy the equations so that I can erase everything else. X squared plus y squared plus z squared equals 4 is the top surface, and z equals the square root of x squared plus y squared is the bottom surface. And we're looking for the triple integral over Q of z dv. To set up the integral in spherical coordinates, let's just remind ourselves of what the spherical coordinates are. X is rho sine phi cosine theta. Y is rho sine phi sine theta. Z is rho cosine phi. And dv is rho squared sine phi d rho d phi d theta. So first of all, let's translate each of these surfaces into spherical coordinates. So this top surface, the sphere, has equation x squared plus y squared plus z squared equals 4. Of course, in spherical coordinates, we know that x squared plus y squared plus z squared is rho squared. So that's rho squared equals 4. In other words, rho equals 2. So let me relabel this now as rho equals 2. And for the cone, we have z equals the square root of x squared plus y squared. So let's maybe first rewrite that as z squared equals x squared plus y squared, and then substitute the spherical coordinates in. Z squared is rho squared cosine squared phi. X squared plus y squared is going to be rho squared sine squared phi cosine squared theta plus rho squared sine squared phi sine squared theta. If we factor out the rho squared sine squared phi, we get cosine squared theta plus sine squared theta, which is 1. So far, the equation for the cone is rho squared cosine squared phi equals rho squared sine squared phi. We'll divide both sides by rho squared and divide both sides by cosine squared. That gives us 1 equals tangent squared phi. So tangent of phi is 1. Now we know that that happens precisely when phi is equal to pi over 4. I don't need to worry about tangent of phi equals -1. That would give me phi equals negative pi over 4, but remember that we keep our phi's between 0 and pi. So I only need the solution between 0 and pi. So the slanted surface is phi equals pi over 4, which makes sense because that cone consists of all the points, so that the ray between the point and the origin makes an angle of pi over 4 all the way around the z-axis. So I think we're about ready to set up our integral. I want z dv. Z is rho cosine phi. dv is rho squared sine phi d rho d phi d theta. And I'd like to point out that if this is a problem on the test, you're already going to get some partial credit for doing this, because it shows me that you've memorized the spherical coordinates as well as what the volume element is. So don't leave any of these problems blank. Fill in as much as you can. This is almost pure memorization, this part. Now let's set up the bound stuff. For rho, I need to start at the origin and go all the way until I get to the sphere. So that's going to be from rho equals 0, which is the origin, to rho equals 2, which is the sphere. Now, for phi, I need to start at the North Pole, which is phi equals 0, and then I need to lean outwards until I get to phi equals pi over 4. And finally, since I want to go all the way around, theta is going to go from 0 to 2 pi. So that's what the integral would look like in spherical coordinates. Now notice that all 6 bounds are constants, and you would be able to factor the integrand as the product of a function of rho, a function of phi, and a function of theta. In fact, let's just go one step further. We could write the integrand as rho cubed sine phi cosine phi. So if you wanted to finish this problem, and I encourage you to do so, you could write this as the product of an integral with respect to rho, an integral with respect to phi, and an integral with respect to theta.